The views expressed in articles published on FIES do not necessarily reflect those of the Illuminating Engineering Society or represent endorsement by the IES. FIES articles complete with figures, diagrams, and graphs can be found in their entirety on the IES website under the Research tab. Please go to ies.org/research/FIES for viewing. Melanopic Green, The Other Side of Blue by Ian Ashdown. Numerous medical studies have shown that exposure to blue light at night suppresses the production of melatonin by the pineal gland in our brains and so disrupts our circadian rhythms. As a result, we may have difficulty sleeping. It is therefore only common sense that we should specify warm light, 3000 Kelvin light sources wherever possible, especially for street lighting. True or false? To answer this question, we first need to define what we mean by blue light. Neither the Illuminating Engineering Society nor the CIE define the term in their online vocabularies. However, UL LLC has recently introduced its UL Verified mark, a third-party product claims verification program. One such verified mark is shown in Figure 1. The verification process for this mark is described thus. In accordance with LM 7908, Section 9.1, measure the radiation emitted by the product across the visual spectrum of 380 to 780 nanometers. From the visual spectrum radiation measurement, determine the amount of blue light radiation emitted between 440 to 490 nanometers. To calculate the percent of blue light emitted, divide the amount of blue light radiation by the amount of radiation measured across the complete visible spectrum. The lower wavelength limit of 440 nanometers seems somewhat arbitrary unless you define violet light, but the upper wavelength limit of 490 makes sense. Wavelengths in the region of 490 to 570 appear to be varying hues of green. This makes it easy. If we eliminate light of all wavelengths below 490, we should not have any concerns about suppressing the production of melatonin and possible sleep disruption. True or false? To answer this question, we need to take a closer look at those medical studies. The human retina has a smattering of intrinsically photosensitive retinal ganglion cells, or iPRGCs. Similar to the more familiar rods and cones, these iPRGCs contain a photosensitive protein called melanopsin. The sensitivity of melanopsin varies with wavelength, as shown in Figure 2. It is these iPRGCs that sense blue light and send signals to the suprachiasmatic nucleus, a tiny region of some 20,000 neurons in the brain that is responsible for instructing the pineal gland when to produce melatonin. Looking more closely at Figure 2, however, it is evident that the iPRGC's spectral sensitivity peaks at 490 nanometers, as well as extending to the ultraviolet edge of the visible spectrum at 380 nanometers. Most importantly, fully half the spectral sensitivity of melanopsin is to green light. Common sense is starting to look rather nervous. The spectral sensitivity shown in Figure 2 is interesting enough, but it becomes even more so when we consider what it means for how we respond to the radiation emitted by white light LEDs. Figure 3 shows the relative spectral power distributions, or SPDs, of typical white light LEDs with correlated color temperatures, or CCTs, of 3000 Kelvin and 4000 Kelvin, scaled such that both LEDs produce equal amounts of luminous flux. Determining the relative response of iPRGCs to these LEDs is easy. We simply multiply their SPDs by the melanopic sensitivity function on a per wavelength basis, as shown in figure 4. Common sense, it would seem, has good reason to be nervous. Yes, 3000 Kelvin LEDs produce less melanopic flux than 4000 Kelvin LEDs when they produce equal luminous flux. However, the difference is only 10%. This is within the tolerance of architectural and roadway lighting design practices. As such, it should not be argued that 3000 Kelvin LEDs are required for nighttime lighting in order to minimize circadian rhythm disruption. The difference in melanopic flux does not support this. Rather, it is simply one of several factors that must be considered when designing and specifying lighting systems. Blue blocking glasses. Figure 4 highlights another issue, the efficacy of blue blocking glasses, which are often marketed as promoting better sleep. If we assume that the yellow filters provide a perfect cutoff at 490 nanometers, they are only 33% effective in blocking melanopic flux from 3000 Kelvin and 43% effective with 4000 Kelvin LEDs. In reality, the filters likely let through some amount of blue light in the region of 470 to 490, and so they may be even less effective. Simply put, we cannot prevent melanopic flux emitted by white light sources from impacting our circadian rhythms unless we use deep red filters. This is not to say that blue blocking filters on eyeglasses or light sources do not work. They inarguably block blue light. However, melanopic flux includes both blue and green light. From a marketing perspective, it is fair to say that blocking blue light may alleviate circadian rhythm disruption and loss of sleep issues, even if it is due to the placebo effect. There are many other psychophysiological and environmental parameters involved in circadian rhythm entrainment that are not discussed here. However, it is incorrect to claim that blocking blue light will eliminate melatonin suppression and so prevent circadian rhythm disruption. The facts state otherwise. Electronic devices. Finally, what about those evil electronic devices that threaten our sleep? Figure 6 shows the spectral power distribution of an Apple iPad and the resultant melanopic flux when the display is set to full white, which has a CCT of 6700 Kelvin, somewhat higher than the 6500 Kelvin white point of most computer monitors. As shown by figure 6, the best any optical filter or software-based change in the device white point, that is, a change in color temperature, can hope to achieve is a 50% reduction in melanopic flux. What is more important, however, is that the iPad screen luminance is approximately 400 candela per square meter. This is on the order of 50 to 100 times the light levels recommended for residential street lighting. If we are to complain about light trespass from residential street lighting into our bedrooms causing sleep deprivation, we cannot ignore the influence of the televisions, computer monitors, and tablets that we often stare at for hours before going to bed, and in much closer proximity. Conclusions. Research into the influence of spectral content and retinal illuminance on circadian rhythms is ongoing. As such, this article should not be taken as evidence, or lack thereof, for the effect of blue light on our sleep patterns. Rather, it is a reminder to look beyond the marketing claims of blue light blocking products and ask what this really means. To answer the question of whether we should specify warm white 3000 Kelvin light sources for street lighting, the answer is, it depends. All things being equal, the difference in melanopic flux between 3000 Kelvin and 4000 Kelvin LEDs is only 10%. This is within the uncertainty of light design practices, and so more weight should be given to residents' concerns, aesthetics, color discrimination, and energy savings when making design and specification decisions. To answer the question of whether eliminating light of all wavelengths below 490 nanometers, that is, blue light, will eliminate Any concerns about melatonin suppression and possible sleep disruption? The answer is clear. False.